For our special project, we will be looking at the exact reactions that occur in Lab F and the heat transfers associated with them. What are we doing in Lab F? In Lab F, our goal was to measure the enthalpy of formation for magnesium oxide in the reaction Mg solid and half O2 gas forms MgO solid. To perform this exact reaction, we would need a bomb calorimeter, which we do not have available. Instead, we can apply Hess's law and use a polyesterene calorimeter, which is much more common and cost effective, to measure simpler individual steps that, when added together, give the enthalpy of formation for the more complex reaction that we want to find. First, let's review what we know about enthalpy. The universe is everything and consists of the system, which is the species in the reaction, as well as the surroundings, which is everything else. We also have learned that the heat of the system is equivalent to the heat of the surroundings. But how do we measure the heat transfer? We can measure this heat transfer by looking at the heat change of the surroundings, which is measurable, and applying it to the heat change of the system. For endothermic reactions, heat is absorbed by the system, which in turn means heat is lost by the surroundings, so delta H is positive. Oppositely, for exothermic reactions, heat is lost by the system, which in turn means heat is gained by the surroundings, so delta H is negative. Since we can only measure heat of the surroundings, which consists of everything except the reacting species, we can apply the change to all of these things to the change in heat for the system. So, how does this occur in Lab F? In our lab, we will be using 3 steps to combine to make our desired reaction. These reactions are: first, magnesium solid reacts with aqueous hydrogen ions to make hydrogen gas and aqueous magnesium ions. Second, aqueous magnesium ions reacting with water to make solid magnesium oxide and aqueous hydrogen ions. And lastly, half oxygen gas reacting with hydrogen gas to make liquid water. When we cancel out elements that are found on both sides of the equation, we are left with our desired equation. First, let's look at magnesium solid reacting with aqueous hydrogen ions to make hydrogen gas and aqueous magnesium ions. In our lab, we used HCl, a strong acid that fully dissociates, to get our hydrogen ions. Then, we added solid magnesium. When this is added, the magnesium reacts with the hydrogen ions to make dihydrogen gas and magnesium cations. When this occurs, the water temperature, or the temperature of the surroundings, rises. This means that the reaction or system releases heat, so the change in enthalpy is negative. Next, the aqueous magnesium ions from the last reaction react with water. Instead of conducting the forward reactions, which is hard to perform, we can use the fact that the reverse reaction has the same enthalpy as the forward reaction, only with the flip sign. So we will react solid magnesium oxide with hydrogen ions. Again, aqueous ACl is used to get hydrogen since it completely dissociates. When magnesium oxide is added, it reacts with the hydrogen ions. The oxygen in the magnesium oxide joins with the hydrogen ions to create water, leaving aqueous magnesium ions. This reaction is exothermic, so the water temperature increases. This means that the enthalpy is negative. But remember that we performed the reverse reaction of the reaction we wanted to determine the enthalpy for. So everything has to be reversed, including the sign of enthalpy. This means that the enthalpy of aqueous magnesium ions reacting with water to make solid magnesium oxide and aqueous hydrogen ions is positive or endothermic. Finally, we measured half oxygen gas reacting with hydrogen gas to make liquid water and found that the change in enthalpy was negative. After all reactions are completed, we can use Hess's law to combine all changes in enthalpy to determine the enthalpy of formation. Looking at the state function for the direct reaction versus the steps of our reaction added together, we can see that the products and reactants are at the same level and that the total change in enthalpy is equivalent. Thank you.